Hello all of you. So in the last lecture we discussed the grand canonical ensemble simulations, and we have said that it is very convenient when we are interested in the phase equilibria, and the reason that we gave was that if, for example, I am looking at two phases in equilibrium, let us say 1 and 2, I want to equate their chemical potentials at equilibrium, and therefore it would make sense to simulate in the constant chemical potential case, because then I can vary the chemical potential and look at the phase equilibrium behavior. For example, if 2 is an ideal gas and 1 is my system, we have kind of a convenient regime where I can do the phase 2 using the ideal gas thing, where I know the expression and I only have to simulate the system, and therefore I can simulate a different chemical potential, and therefore we can find when will we have the phase equilibrium condition. However, in the grand canonical ensemble, the volume and temperature are also controlled. In most realistic cases, when we have an open system, it is not really the case, because let us say, for example, we are looking at an open system containing water in contact with air, where water can evaporate and go into the air. So, in that case, clearly if water forms a phase, a thermodynamic phase, then the volume of water is also not fixed. So, what would have been more convenient is, so we can keep the chemical potential a control variable or chemical potential constant, but we can let the volume change, because volume in the phase 1 is changing here, and the same is true for other cases of phase equilibrium we can imagine whenever we have an open system, and therefore we want the volume to change. We can work at constant temperature. So, ideally we want to work as something like a mu pt ensemble, where volume may also vary and I can work at a constant chemical potential. So, it turns out that mu pt is not really a valid thermodynamic ensemble, because all of these are intensive variables. So, there is no variable containing the system size, and therefore we cannot really work on that. Something closer to that we can achieve using a method called the Gibbs ensemble method, where the volume is allowed to vary, but then we are also simulating the system too, and in some sense it is good, because we do not have to assume that the system 2 is an ideal gas. So, we have 1 and 2, and these can be pretty much anything, but the volume of each of these systems can change and the chemical potential can be held constant or a controlled variable. So, it is something that looks like a mu pt ensemble in principle, but it turns out that it is indeed a canonical ensemble still in some limit, and I will not go into the math behind it, but it is just some approximation of the canonical ensemble. Under some limit, this gives me the canonical ensemble behavior. So, the idea here is that I assume a large box, and the large box is at constant volume and constant number of molecules, and there are two parts of the box. You can imagine there are two boxes, if that is more convenient, and the two boxes are in contact. So, they are exchanging molecules, but they can also exchange volume. So, they are doing both the volume change and the molecule transfer between each other, right. And now I am simulating both these boxes, right. So, let us say this is my box 1 and this is my box 2. I am simulating both of them. So, I am basically able to transfer molecule from one box to the other, and I can transfer the volume, or if I decrease the volume in one box, then I increase the volume by same amount in the other box, and vice versa. Both these boxes are being parallelly simulated. This is a very intelligent method by Panagiotopoulos, but now it has been used for a variety of calculations of phase equilibrium. It turns out to be like one of the most commonly used methods for phase equilibrium. particularly in the liquid like media. So, we are simulating both of them, and then the kind of movements that we make in the Monte Carlo algorithm is I start with the two boxes 1 and box 2, and there can be individual particle displacement in both of these boxes. So, in this case, for example, one particle in box 1 is moving and one particle in box 2 is moving, right, and both of them are pretty much happening together, right. Then there is some volume change. So, if box 1 increases in volume, then box 2 decreases in volume, and finally, there can be an exchange of particle. In this case, a particle from box 2 is coming to a location in box 1, and this process is continued until we get the condition of equilibrium, in this case the phase equilibrium. So, this is the basics of the Gibbs ensemble simulation. I will not go into the detailed numerical implementation of that, but I would refer to the book by Frankel and Smith that has, I would say, the detailed algorithm and description of what exactly is a theoretical foundation behind the Gibbs ensemble. One of the other methods that is particularly convenient for mixtures and along the lines of what we have discussed is the following. So, it is called the semi-grand canonical ensemble method, and in this case what we do is we start with a system containing a binary system of particles. We can have more than two components as well. In this case, this white guys are one component and black guys are another component, and what we do in the simulation along with particle displacements are we change the identity of the particles in the simulation. So, you can have a Monte Carlo step where particle of species 1 become particle of species 2 and vice versa. Now, this is not really happening in the physical sense because Monte Carlo is not looking at the true dynamics. This is only happening in the artificial sense because I am interested in the equilibrium composition of the mixture, for example, at a particular chemical potential and so on. And therefore, we can do this kind of artificial displacement and we can keep on doing it and find the composition of individual phases at different chemical potentials and so on. And the method is called semi-grand canonical because the total number of molecules are fixed, but the number of molecules of individual species, let us say species 1 that is N1 here and species 2 that is N2 here, they can change, but their sum has to be constant and therefore, we call the name semi-grand canonical ensemble. So, all the methods that we have discussed so far, they were focusing on the phase equilibrium problem where I want to look at the coexistence behavior of the two phases. We have discussed the grand canonical ensemble, the Gibbs ensemble and semi-grand ensemble. Now, I want to come to the general problem of the free energy calculations, because if I can compute the free energy, not only I can look at the phase behavior, but also it is important to look at phase transition in more general and several other cases where we have large free energy barriers and that cannot be simulated within the conventional Monte Carlo or molecular dynamics simulations. The first question, however, that we can pose is why did we not compute the free energy in the conventional Monte Carlo or molecular dynamics? Because we have been sampling the phase space. So, in principle we should have had the partition function because all the averages that we had computed, all the canonical or other averages for different ensembles that we have computed, they were done by already an integration over the dr and dp variables in the phase space. Then what is the problem with the partition function? And the answer to this lies in the fact that we have always preferred to choose configurations which are of lower energy. That is, in the metropolis algorithm, for example, we assign more weight to the configurations that have higher probability, that is larger value of exponential of minus beta u. So, that by default ignores many configurations that are of higher energy. On the other hand, when we look at the partition function, it is not difficult to see that the higher energy configurations have a big role to play in the partition function itself. So, let us say for example, I start with the configuration part of the partition function, that is simply an integral of exponential of beta minus beta u. I can rearrange in the following way. So, I can write the ideal gas part that will correspond to essentially u equal to 0, and I can divide again by the same quantity drn, but instead of 1 I have put e to the power beta u multiplied with e to the power minus beta u, and then whatever we had here, that goes in the denominator of that. And this rearrangement tells me that the denominator of this expression now is basically, if you look carefully, is the canonical average of exponential of beta u, because in general average of any property is drn exponential minus beta u m divided by drn exponential of minus beta u. The denominator is the partition function. If I put m equal to e to the power beta u, I will get whatever we have in the denominator here, and the numerator already is, we have said, is the partition function of the ideal gas. We are not keeping the prefactors here because they anyway cancel out. So, what this means is the partition function of a system can be written as the partition function of the ideal gas that we can compute analytically multiplied with 1 over the canonical average of e to the power beta u. Now, clearly this quantity is going to be large when u is large, and in metropolis algorithm we are actually giving less preference or less importance to the large energy configurations. So, the parts of the phase space which are contributing to my canonical averages are the parts which are having lower energies. On the other hand, the parts of the phase space which are contributing to my Q includes the larger u's as well, and therefore, we never really compute the partition function, or I will not say that it is impossible to compute, but it will be very time consuming affair to compute the partition function of the canonical ensemble. And one of the reasons is because you have too many states of larger energy that has to be considered, and since e to the power beta u is an exponential function and there are plenty of states of large energy, this calculation will take very long. I mean, we have to take many Monte Carlo step, and of course, we have to modify the metropolis criteria because that by default assigns more importance to configurations of lower u, and in this case we want to give importance to higher u configuration because those are the ones which are contributing significantly, or I would say mainly, to the partition function. So, then clearly we do not compute the q, and therefore, although we said that q is a generating function and once we have q I can get f, that approach is almost never followed in any molecular simulation. Instead, what we typically do is we work with the derivatives of the free energy, and in most cases those are some things that we can easily get from a molecular simulation. For example, the average energy we can easily compute in a molecular dynamic simulation, let us say performed in the NVT ensemble. We can simply compute every energy of every configuration and then average over that. That quantity is given as the derivative of the ln q with respect to beta, where beta is 1 over kBt, or we can write that as derivative of f by kBt divided by derivative of 1 by t. Now, this is something that we can easily get because average energy can be computed in a simulation. In a similar manner, I can find the average pressure, that is again a derivative of the ln of the partition function and also a derivative of the free energy, because F is simply minus kBT ln Q or minus ln Q by beta, and therefore, I can easily compute that derivative. Now, once we have the free energy derivative, we can find the free energy differences from any particular state. Now, let us say you have a reference state for which you know the energy, for which my F is known. Now, if I am looking at some other state where I am interested in, although I cannot find the free energy of that state directly, if I am able to imagine a path between these two states by changing, for example, volume and temperature, since we know how the derivatives of free energy with respect to volume are and how the derivative with respect to temperature are, we can basically find the free energy difference of the state from the reference state. In this case, F minus F ref, that is delta F, this is something that we can compute. Now, the interesting thing here is that reference state is completely arbitrary for us to choose from. It does not have to be physically a reference state where the system is coming from. It can be any arbitrary state. Let us say, for example, I can say my reference state is a perfect crystal at 0 Kelvin or an ideal gas at a certain temperature. It is completely up to us how we can choose the reference state, as long as we can define a path from that reference state to the current state of the system in the volume temperature plane, that is by varying the volume and temperature. If I can get from the reference state to the current state, I can find the free energy difference, and once I find the free energy difference, I can find the absolute free energy of a given state. And since free energy is a state function, it does not depend on the path. So, if we would have started from somewhere else, or if we would have followed some other path to get here, let us say I follow some other path, or let us say if I come from somewhere else to here, it does not really matter. The free energy in that state is completely independent of where I came from and which path did I follow, because it is only a state function. The only reason why we are introducing a reference state is because we know the free energy value there, and we can pick any of the reference state for which the free energy value is known. That also means that even the choice of path can be completely arbitrary. It may not be really a physical path that is being followed in the experiment, or that can even be created in the experiment. It can be a completely arbitrary path, as long as it is connecting the two states and as long as it involves the changes in the volume and temperature, whatever variable that we are looking at, we can find the free energy in the state of interest. And this is precisely what we do in the method known as the thermodynamic integration. So, the way we do in this particular method is we start with a reference system 1, and for that reference system or the reference state, I know the free energy. This can be an ideal gas system, that is kind of example that we have discussed earlier, or this can be a perfect crystal or an ideal liquid or any other arbitrary reference state for which free energy is known to us. And system 2 is my system of interest. And now, we typically define a linear coupling parameter, although it can be any other relation as well, going from 0 to 1. So, lambda is a coupling parameter from 0 to 1, and I introduce the energy function u lambda as 1 minus lambda u1 plus lambda 2 lambda multiplied with u2. Sorry for the typo, it's lambda, right. For lambda equal to 0, my u lambda is equal to u1, and for lambda equal to 1, my u lambda equal to u2. So, basically we are imagining some path along a variable that we have defined, right. So, we are saying that the energy of the system or the interactions between the particles are changing in this particular arbitrary way. Now, as I said, this need not be a physical path, because you may not be able to envision systems at which interactions have this particular value linearly changing in this particular way. Let us say, for example, I can say that if I want to simulate a system interacting with a Lennard Jones interaction, let us say if it is given by some particular functional form, and let us say if it is the only interaction in the system, what I am trying to say here is that I will envision systems where the u is multiplied with lambda. So, for lambda equal to 0, we will have no interaction in the system, so it becomes an ideal gas, and for lambda equal to 1 becomes the system that we are interested in. So, for all the intermediate lambda value, those systems we do not need to create or do not need to be there to be able to use the thermodynamic integration. The path can be completely arbitrary as long as it is mathematically valid, and that is indeed true in this particular case. We can assume other kinds of function apart from a linear function, but in this case we are assuming a linear function of u with respect to lambda, and we will change the interactions. You can imagine that I can slowly turn on the interaction in the system. So, if my system is Lennard Jones, we slowly turn on the Lennard Jones interactions. If Lennard Jones system is my reference state, I can have some other interaction on top of it, let us say a Coulomb interaction. Then I will slowly turn on the Coulomb interaction by multiplying the Coulomb interaction by lambda. So, I can pretty much work in steps. So, let us say for example, I want to simulate a system where we have both Lennard Jones and Coulomb interaction. Now, in the example I did previously, I was doing a Lennard Jones only. So, the ideal gas was the reference state, and I was slowly turning on the Lennard Jones interactions. Now, the Lennard Jones system can be the reference state. For lambda equal to 0, there is no Coulomb interaction, and as I change lambda and I finally become lambda equal to 1, then in that case we have the full Coulomb interactions, and we can imagine many simulations being done at different lambda values along these paths. So, clearly this means that the method is quite time consuming, because we do not have to do just one simulations, we have to do many simulations at the intermediate lambda values along the path. With that particular introduction, I want to conclude here. In the next lecture, I will go through the numerical implementation of the thermodynamic integration scheme, and then we discuss other methods of free energy calculations. Thank you.